Welcome to example number 8. It's a question involving the work done by a spring scale. So we have a woman that steps onto a scale. She has a weight of 600 newtons, and there's a heavy spring embedded within the spring scale. And so when she steps onto the spring scale, the spring compresses a distance of 1 centimeter. And we're asked to determine the force constant, which is known as the spring constant. And we're also asked to find the total work done during this compression. So we know in here, as our given information, we're given that the spring has compressed a distance of -1 centimeter, or you could write that as -0.01 meters. Now the weight of the woman is 600 newtons. And so if you look at this object here, the top surface of the spring scale, we have really two forces acting on it. There would be the force of gravity of 600 newtons downwards, and then we have the spring scale acting in the opposite direction of 600 newtons. Both of these forces would be equal to each other because everything is in equilibrium. So if you remember from Hooke's law, the force of compression, or the spring force, is directly proportional to the displacement, which more specifically, the spring force is really equal to -k times x. So therefore, if you want to find the spring constant, k would be equal to negative of the spring force divided by the displacement. So that's -600 newtons divided by -0.01 meters, and this gives you a spring constant of 6.0 times 10 to the power of 4 newtons per meter. Now, by the way, I often neglect the negative because I find sometimes people get confused with all these negatives. So you could have just solved this problem and just write spring force equals just positive kx and used k and then a distance of 0.01 meters and then 600 newtons. And then you'll get the same answer and just neglect the negative. It doesn't matter to me. Okay, it does matter later on when we're dealing with simple harmonic motion, but don't worry about it at this point. So that's part A. Okay, so we're now moving on to part B. We're asked to find the total amount of work being done by the spring. Now there's a variety of ways that you could do that. You could, say, plot a graph where the force is directly proportional to the displacement, and then we can put in some values here. And the work done by the lady pushing down on the bathroom scale would be equal to the area under the force versus displacement graph, which would be equal to 1/2 the base, which is 0.01 meters, times the height of this triangle, which is 600 newtons. And this would give you an answer of 3.0 joules. Or alternatively, you could use a non-graphical approach and just say the work done would be equal to the energy that is stored in the system. That would be the spring potential energy. And the formula for the spring potential energy is 1/2 times kx squared. So it's 1/2 times the spring constant, which we achieved before. It's 6.0 times 10 to the power of 4 newtons per meter, multiplied by the displacement of 0.01 meters squared. And this gives you an answer of 3.0 joules as well. All right, and there are probably even other ways, but be careful with using a formula such as the work done equals the force multiplied by the displacement multiplied by the cosine of the angle. If you were to use her force of 600 newtons multiplied by the displacement of 0.01 and the cosine of 0 degrees, you would get an answer of 6 joules, which is incorrect. Because the reason is that when she starts to step onto the scale, the spring scale is, as it's being compressed from 0 to 0.01 centimeters or 0.01 meters, it's not a constant force acting. Yes, her weight is constant, but as the spring is being more and more compressed, there's more and more force. So really, if you were going to take this approach, you should be using really the average force. And the average force would not be 600. That's the maximum force at this displacement. The average force is 300 newtons. But I don't really like using this method. This would obviously give you 3 joules, but be careful with this formula. This really, I think you should only be using this when you have a constant force. Okay, and that's it for example number 8.